Hello, everybody. My name's Tom. I'm not giving this talk. I'm just introducing them. But first, make sure you're in the right room because there's been a swap. So if you were here for the day in the life of a Kubernetes contributor, that's next door. But the slide's been up for 10 minutes now, so hopefully you've got that. So I'm here to introduce David and Stefan, both from Red Hat. I'm really looking forward to this talk. They asked me to be on the program committee and review a bunch of talks. And the reason I selected this one is I've had exactly the problems that they're about to describe and show hopefully the right solution to. So round of applause, please.
Hi, so I'm David, and this is Stefan. And we're talking about how to manage a Kube-API server. And one of the ways that a lot of people have tried to do it is by running the platform on the platform. We are here today to talk about how we started, our experiences from there, how we started the second time, and where we actually ended up. So we started out with these goals. We want to be able to make config changes, we want to be able to do upgrades, and we want to be able to handle cert rotation, all without having hiccups on the Kube-API server. We looked at the existing technology that was out there. Bootkube existed. It looked like a really good idea. They start out having a set of static pods that they use for bootstrapping their cluster. So you have a static pod, which is a pod that runs on the kubelet without any other resources being present, no active Kube-API server at all. It runs effectively a container for you, and the container runs whatever process you want. So you start out with a static pod for a Kube-API server, and you have one for a kube controller manager and a scheduler, and from there, you create real workload resources. So you create resources for the Kube-API server as a daemon set, for instance, and it rolls out using the control plane that you have. This works very well. It starts up, it runs, the pods are roughly equivalent, and you then remove your static pods. So you started out, you had your table set, and then you just pull the tablecloth out. Everything stands up and keeps running. The idea is that you're going to use the workload resources we developed in Kube to roll out your future changes. So you're going to make a change to a daemon set. Daemon set rolls out onto all the nodes. Nodes recycle, and you have upgraded. And this works pretty well until you crash. But Bootkube thought of that. So we have a static pod checkpointer, right? So in case you crash, there's going to be something for you to start back up with. Now, static pod checkpointer, how does it work? It looks at the config maps and the secrets and the other resources you have for your daemon set pod and creates mirrors of those on disk. You never actually run them, but you have a pod YAML that you think is going to work when you replay it, right? So the idea is that if everything goes down, you find your static pod YAML, you start over again, rebootstrap, repivot. So one day I had a bad day. We were working on this project. I had my 3 nodes, 3 kube controller managers. They're all running happily. And if you know much about the kube controller manager, you have a health check, which you must pass, or the kubelet will kill you. And then you have a lease. The lease is what the kube controller manager does to make sure only one is running at a time. And it's very important, but what it means is that you actually have idle processes running. So you have 3 nodes, only 1 is doing work, 2 are just idling and waiting, but they are reporting healthy. So I go to roll out the next version. I've made a change to the kube controller manager, and I start rolling it out with my daemon set, and things are going well, right? First pod rolls out, goes on the node, says that it's healthy, doesn't acquire the lease. One of the old ones is still running it. Daemon set controller's still running, I get my second pod. Second pod comes up fine, reports healthy, it also gets checkpointed. It doesn't have the lease. Third one updates. And now, my very first one that I rolled out acquires the lease, and oh my. It dies. It had a bug where, it doesn't matter what it was, it panicked and it died. And at this point, the next lease gets acquired. Don't worry, I've got this, and oh dear. And we end up in this state. So I'm in this state, and I say, oh, that was bad. Well, I'm just going to roll back. So I roll back my daemon set change, and nothing happens. And being a bit slow, I sat there and I stared at it for a while. this is weird. What has happened? And it turns out that without a daemon set controller running, the daemon set to put my daemon set back didn't work so well. So I go, okay, don't worry. I'm going to go back to my static pods. And I go to my static pods, and they've all been checkpointed, and none of my static pods run. And at this point, I rethink my life. And I come up with an alternative, right? I decide the solution to my problem is actually to have static pods that are always running as static pods. And this lets me avoid a pivot. I never have to figure out how to go from a static pod to a daemon set, back to a static pod, and then how to restore it, because that process usually works, but it's not foolproof, like I just found out. Then, using static pods, you're tolerant to cube failures. You don't have any cyclical dependencies, right? So the main point here is that when I experience this problem in the future, I don't have to worry about my daemon set being up in order to fix the daemon set for my kube controller manager. So how did we do it? We have an operator that manages static pods for us. And the way it does it is it has this idea of a revision. There is a set of config maps and secrets, and they're an immutable set. So what happens is you have a live set, you observe a change, you copy them over and make an immutable set, and we call that a revision. And then we have a cheat. We have an operator that runs and creates an installer pod. That's how we actually get the files down onto the node that we want. And when we do that, we create this installer pod and we force it directly as a pod, explicitly labeled for a given master. What that means is that we don't depend on the kube controller manager and we don't depend on the kube scheduler. So once the installer pod is there, it copies the secrets and config maps down onto disk and then creates a pod YAML and places it into the kubelets manifest directory. So the static pod then starts to run. Before the operator moves on to another node, it makes sure that you're healthy. So what then happens for the deployment of Doom? What would happen in this scenario? Everything would still get updated. All those pods would still crash. I would still end up with a picture that has everything crashing, but because I have this installer pod, which is force scheduled, and because I have an operator which is still running, I can make a change and deploy a new version and recover my kube controller manager in place. This is much easier for us to manage overall. The other property that you get from this is that by carefully naming your static pod resources, you're actually able to have the previous revisions that worked for 5, 6, 10, whatever you want, number of successful revisions located on the kubelet that you have. This says the same thing in words if you're following along at home. And here I will leave it to Stefan.
Yeah, so I highlight our theme here without hiccups. So what does it mean to run API server without hiccups, without errors for the user? So the user shouldn't notice that we roll out a new revision. And so we summed that up in clients don't get immediately dropped. So clients keep running the requests, getting answers. They don't notice at all that there's a rolling update going on, for example, for a third rotation we will see later, or for configuration changes or upgrades. Make sure you are not ready but healthy. I will show details in a second what that means. Make sure that the load balancers don't send traffic to the pod which goes down. And I highlighted really here. So this is not so easy in real cloud environments where the spec of a load balancer specifies 30 seconds, but after 35 seconds, sometimes you still get traffic. Really make sure and adapt your timeouts in a reasonable way. And make sure that the service network, so everything which is in the cluster, doesn't send traffic. So IP table rules from kubeproxy should be up to date. Sounds easy. In reality, it's not really that easy. So I put some logs. Everybody will know those kinds of errors. And those are excerpts from our CI system. So we wanted to avoid hiccups in CI during test runs usually. And you see those errors in the logs. And other teams get, they don't like to see those errors. And when there's a connection refused, they complain to us. What are you doing? Why is the Kube API server not ready, not answering my requests? So the first one is certainly something we have to fix to claim we don't have hiccups. The second one, go away everybody might have seen that already. It's an HTTP 2 protocol message we see, but it's about watches. So we have stream watch here somewhere in the logs, which is a good hint. It's about watches, and watches can go down. We have code for that to cope with closed watches and restart them. It's not nice, but it happens, and we can cope with it. We don't have to investigate anything. The third one is end of file. So there's a request going on. It's not really answered properly, and in the middle of the request, connection goes down, something we don't want. And I highlighted here already a term. It's called long running and non-long running or short running requests. A watch is by definition long running, so it's infinite if everything goes well. A post, like in the third example here, it's written post, it's short running. So we expect an answer within at most 60 seconds. And the fourth one, it's also end of file, but again, it's about watchers, so we don't care. They go down when an API server really terminates at the end, so this is completely normal. Of course, there are errors where nobody really knows who to host. It's some network issue, probably not really related to terminating Kube API servers. So we have two cases we have to investigate here. And that's where we come to graceful termination. So for some time in Kube API server, we have this concept, so we can gracefully terminate. And gracefully terminate means, yeah, we have requests going on. So here's a timeline in the middle. So from left to right, at some point, we get a SIG term from kubelet. We are asked to terminate. And there's a request, a watch going on, the blue line, and it goes up to the end when the termination really finishes. It's fine. I have a green bubble here, so we accept that. All right. There's a list. Started very early. It takes ages, like 60 seconds. After 60 seconds, it's killed anyway. So if a request takes so long, something is wrong, etcd is under too much load, we accept that. It's also fine. But here are short-running requests like a get from inside of the cluster. It's the green one, and the second one here, it's from the load balancer. They are answered until certain points when we get errors, so those red bubbles. The critical time here is the yellow one. So we receive our signal. The API server removes itself from the endpoints. It doesn't have to wait for the kubelet to do that or for some controller to do that. It does it automatically itself. That's fine. And it stops listening. And stopping listening means every request which comes in now gets the connection refused. Not so good. Because kubeproxy takes time to realize that. External load balancers need time to realize that this server goes down. So in this time frame, we get errors. We don't want them. So graceful termination is not enough. Actually, yeah, the first idea is, yeah, why do we stop listening so early? Let's move that far to this place here, far after kubeproxy and the load balancers noticed. Yeah, we can do that. We cannot do it now, so Kube API server doesn't allow it, but we added something called minimum shutdown duration. That was a quick fix. It's not merged yet, but it helps. It delays the termination. So Kube API server knows there's a signal I have to shut down, but it keeps running and answering everything for 30 seconds, for example. The API server takes out the IP from the endpoint, so the kubeproxy will notice, and internal cluster clients will eventually, within those 30 seconds, not send traffic anymore. External load balancers, yeah, you have to tell them somehow, more in a second, what this means. And after 30 seconds, no traffic comes in anymore, so you can shut down and stop the connection. Not shut down, actually. Graceful termination means that we still process all requests which are in the stack. So every request which went in HTTP server in Golang is still processed, and when there's no request anymore in the pipe, we really terminate. That's graceful shutdown. And if we do that, this critical phase here becomes gray, so it's not critical anymore. We stop listening after our system around has adapted. There's one point missing. How does the load balancer really know about that? First idea, we have health C, so the health check endpoint. Health means kubelet will kill us if it's erroring, so we cannot really send anything else than 200. Otherwise, we are killed earlier. So we need something else. And there's something well known in other areas. It's a second endpoint for readiness, ready-z. Again, we don't have that today. We might want that because otherwise we cannot implement something like that. The load balancers should listen on ready-z. And this goes to an error code immediately, but the API server is healthy and keeps answering for 30 seconds. But the load balancer has a chance to notice that and adapt. And then we can do graceful termination. And that way, we realize this gray box really for all situations. So why do we do all that? Without hiccups as a theme. Config changes, upgrades, it's clear for everybody. And we want to talk about search rotation a bit more. So we have this nice mechanism we can roll out without any dropped connection. Let's use it. And search rotation is something, it's perfect for that.
So, cert rotation. Everyone loves cert rotation day. I'm sure none of us have ever had an issue where I forgot to rotate those and oops, it's down for the whole company. I was going to go ahead and start this section by looking at the flags that were available, and so I pulled them up. And with a little description, they don't fit so well, and that is actually the smallest font Google Slides will allow you to use, and they still don't fit. So rather than starting there, we will talk about how individual chains are managed. So Kubernetes has a lot of chains, lots of flags, and it's not always obvious why we have them. And what you see here is a mutual TLS connection. And what that means is that the server verifies the client and the client verifies the server. And I'm going to very briefly go through how that works. So a client has a cert and a key, and he uses that to identify himself to a server who has a client CA bundle, which he uses to verify the client's identity. Server then responds back with a serving certificate, cert and key, that the client has to be able to trust using a server CA bundle. Now, what you'll note about that is that if you make that into flags, that's a bunch of flags, that you have to get all these flags, right? And as you rotate, you have to be sure you get them updated in the correct order. So if we look at a specific example, one that you're going to have to manage when you're trying to manage your control plane of static pods and manage the cert rotation, is the Kube controller manager speaking to the Kube-api server. And all these flags exist. You have the cert key for the client, you have the CA bundle, and when you update, you always have to remember to update the CA bundle first, and you have to be able to orchestrate the change. So you have to handle the fact that all the Kube-api servers have to respect the new client cert before you give it to the Kube controller manager. If you accidentally get that wrong, your Kube controller manager gets 401s, and bad things happen, right? Same thing happens on the server CA bundle side, right? You have to make sure that if you're managing a set of internal certs, not the external ones, but a set of internal certs, you need to make sure that your clients have been updated to respect the new one first. So now that we know all the different certs that we have, and we repeat this chain, I don't know, 4 or 5 times for different components, you also have to understand the relationships. So as you go to manage a relationship, you can't just change a flag in a vacuum. One of the really common ones that you want to turn on, it's a best practice, is rotating the certificates for kubelets. For the client certificate that they use to connect to the Kube-api server, and for the serving certificate that the Kube-api server uses to trust the kubelet. And you'll do this for all sorts of reasons, but you have to get it right. If you start by setting the rotate flags on the kubelet, because that's the feature that I want, you'll start back up, and you will have a kubelet that crashes. Well, it starts and it waits, and then it crashes, because it can't make forward progress. Because the controller manager that it expected to sign it isn't signing. So you then had to know, well, I have to set this flag in the Kube controller manager. So you go ahead and set the flag in the Kube controller manager, you get a signed certificate back to your kubelet, you launch your kubelet, and you never get any pods. Not a single pod goes to that kubelet. You look in the logs, the kubelet is filled with 401s because you forgot to set the Kube-apiserver client CA file. So you now have to add the correct certificate from your kube controller manager to your Kube-apiserver, add it to the CA bundle so that the kubelet is recognized. And at this point, you think, hey, I've got this all working. It's great. Until you try to go pod logs, and those suddenly fail. Pod logs are failing because you forgot to set the last piece, the kubelet certificate authority. The Kube-apiserver validates connections, verifies connections to kubelets. And if you forget to set this flag to respect the signer, your cluster still won't work. So we're looking at all these flags, 30 some odd flags that have to get set, that all have to be coordinated. And this is why we look at it and say, well, we're going to have an operator manage this. Because in the end, you set all these flags, you have all these relationships, you had to make sure that the bundles were set correctly, and you orchestrated the updates so that you did everything in the correct order. And what did the cluster admin care about? He cared about one thing. He wanted to be able to bring the one cert that he paid for that is signed by Let's Encrypt or whoever it was, so his Kube-apiserver could actually be trusted. That's the one flag he wanted to set. And so we can take over management of all the others. And it makes it much easier and safer to roll out changes overall. So where do we end up? We managed to create a flow that has a Kube-apiserver or any other process managed by static pods, roll out their changes over time, changes to the configuration and to the upgrades and to the cert rotation, all happen without dropping connections on the floor and rolling out cleanly on a self-hosted environment. Anything else to add? All right. We will take questions if you have them.
Thank you very much. Sorry if I go with the first question. I'll bring the mic around afterwards. How do you do the root of trust for the operator?
So trust for the operator. When the operator comes up, it runs as a regular pod. So you have static pods to launch, and then the static pod is equivalent to the very first static pod that you're going to use. Once you have that, we have a signer in the cluster that we can then distribute to any other pod with the service account CA bundle. So the operator trusts based on that, and then any additional trusts the cluster admin can choose to configure, but they usually don't have to.
I'll just go one quick follow-up. How do you then rotate that?
So rotation for that piece happens the same way. So there's actually a signer located. You can drop a new signer in the secret, and then when the new signer is available, it will immediately get added to the CA bundle. CA bundle will then ripple out across all the pods. We then sign the new serving cert. Serving cert ripples out.
Thank you. Who else has a question? Come on, somebody's got to have a question. Awesome, thank you.
So I know that it's a good practice to have different certification authorities for example, etcd and for apiserver. So do you do that, and what's your recommendation?
Yes, we do. So once we figured out how we were able to rotate one of those mutual TLS pieces, we were able to apply that same practice to all the different ones. So we have, we actually even have multiple signers for clients and as well for servers. So every single chain of trust that we have is distinct.
You're going to make me run all the way to the back, Lucas? Oh, I don't normally run.
Thanks. Sorry if I missed it, but is that operator open source?
Yes, it is. This is an operator in the OpenShift org. It's the OpenShift cluster Kube-apiserver operator. It's a mouthful. We have them for each of the control plane components. You can look at them there. You can use them if you wish. They all make use of the same library for managing static pods, right? Because we had to manage multiple different static pods. We have a little library to develop an operator that can do that and handle the rollout that we showed at the beginning.
Right, thanks. And how far are we in getting declarative configuration to the components itself or themselves? Did you fix that problem with the operator? Like, can you manage the operator in a declarative way, or are you still just applying flags to the API server and controller manager itself?
What we do, we have a higher level configuration, which is then translated into the flags or whatever the component takes. So we have a very high level configuration for that, whereas there's not, it's not a flag level, it's higher level. We don't do component configs beyond what upstream does. So.
Okay, but you figured out a way to do it a higher level thing anyways. So
yeah,
that's a good starting point.
I think that's a subject for a different talk, but yes. Right. You do have to have someone orchestrate.
Cool. Anyone else? Hands up. Wave them back if I missed them. No. Awesome. Thank you very much. Big round of applause.